Hello, my name is Jeff Ryan and I'm the Regional Science Coordinator here at Olympic ESD. Welcome to session 1 of this 4-part professional development online series here related to teaching and learning systems in a science classroom. This is what is a system, and what I'd like to do here in this segment is just begin the conversation about what a system is, share a few things with you, and get you ready for the next module here. Go ahead and let you know what you'll need. First, you're going to need a Washington State Systems Standards at a Glance handout, which you can find on this webpage. You'll need a notebook like this, or some paper and a pen, something to write with, or a pencil. And then also the Habits of a Systems Thinker handout. And that will do it. And we'll go ahead and start here today with an elicitation question. So hopefully you can see this slide good enough. And what I'd like you to do right now is, you don't have a handout of this, but I'd like you to take your paper and go ahead and answer this particular question. So this has various things that are listed, and it asks you to put an X in front of the things that you think can be thought of as a system. I'll let you go ahead and read that list there. And if you want to make it easier on yourself, you can just list the things that you think couldn't be thought of as a system. But that's not the only thing I'd like you to do. I'd also like you to explain your thinking. How did you decide whether something is considered to be a system? That's the real important part of this particular question here. If you're working with a group of people more than yourself, what I'd like you to do is, after you individually finish this, go ahead and have a conversation with the people around you before you move on, and then I'll provide a little bit of explanation as we go forward. So go ahead and pause the video. Okay, welcome back. Hopefully by now you have spent a moment or two on this assessment probe here. Just as a point of reference here, let me get this advanced. This particular assessment probe, Is It a System?, is from Paige Keeley's Uncovering Student Ideas in Science series, 25 new formative assessment probes. This is volume 4, page 81. And here is, so you get this done here. So here's a basic, here's a basic definition of a system. Now this actually comes from our Washington State Science Standards. Systems, an assemblage of interrelated parts or conditions through which matter and energy flow. That's okay. But here's a little bit more robust of a definition. Two or more parts interacting to function as a whole within some boundary. The elements and processes of a system interact and affect one another, often in ways we cannot see. And in systems, the relationship among the parts matters. If elements or parts of a system are added or taken away, the behavior of the system changes. So let's go back to our original list. So which of these, assuming that we buy into those two definitions here, many of these can be checked here, with the exception of, there's one here, a box of nails. Now, you can probably make an argument for why a box of nails might be considered a system. Is it interacting parts or what? And then also a pile of sand. Depends on where that pile of sand is. But about everything else here definitely can be thought of as a system. Two or more parts interacting to function as a whole. But the pile of sand, box of nails, I'm not so sure that you can make a strong argument for that. So, given that, so that basic understanding of a system, this is a snapshot of the Washington State Systems at a Glance document that actually I'd like to reference Kirk Robbins, the former Regional Science Coordinator at Puget Sound ESD who put this sheet together here. And this is nice because it just takes all the system standards and puts them in one place here. And in this definition over here, this comes from Project 2061, Science for All Americans, and gives the definition of systems here, which I won't read to you, but you're welcome to look through. It talks a little bit about the development and what we want with kids as they start in elementary school. And you can see down here in grades kindergarten, first grade, that systems thinking needs to start early with just a simple understanding of part and whole relationships. So just having students identify the parts of a chair or a table or whatever system you're studying. You don't need to use the word system, but having them identify and recognize that when you take away a part from a whole, that it affects the function of it. And then if you move up to grades 2 and 3, the role of each part in a system, so how objects, plants, and animals are connected and work together, structures and functions, of different parts for animals and plants particularly at the second and third grade level, so having them make observations of systems like a plant or an animal, a crayfish or something, and recognize each of those parts. And as we move up the grades, 4th and 5th grade, complex systems, analyzing a system in terms of subsystems and functions, so that thinking gets a little more complex here. We can talk about river systems now. Some reference to the water cycle as a system, of course. And then grades 6 through 8, inputs, outputs, boundaries, and flows are added into the mix. And you can see 9th through 12th grade, predictability and feedback loops with respect to systems, creating realistic models. And then the big idea is a way of thinking that makes it possible to analyze and understand complex phenomena. And that brings me to this point. Why would we want our students thinking or systems thinking in terms of systems, especially in science? And I think there's a lot of good reasons, one of which complexity in many science fields has increased over the years. Therefore, to understand the complex phenomenon, you have to have these systems thinking skills in order to make a go of it. You need to be able to have had those foundations from an early grade to be able to understand some of this more complex understandings in science. These complex problems and phenomena require systems thinking nowadays more than ever, whether it's in systems biology or engineering with respect to the complex systems that engineers deal with. It's very important. And as the point I made earlier, system thinking habits must be taught beginning in the primary grades. And lastly, issues that face our society now more than ever require a citizenry that understands complex behaviors and cause and effects relationships. As an example, let's look at climate change and human-caused global warming. And that's one perfect example of where having students that are able to understand these complex cause and effect relationships and recognize the inputs and the outputs into various systems is very helpful nowadays. So this is more reasoning for why systems thinking is so important. This has to do with supporting students developing causal explanations of complex phenomena. So one of the primary role of the science teacher then is to help students put together these explanatory models for how the world works. And it's best approached with allowing the student to explore a phenomenon, whether it's in a hands-on experience or in some kind of discrepant event or something, and then up to the teacher to provide appropriate evidence so that the student can make sense of that complex phenomenon. So when you focus on a defined system, that allows you, the teacher and your students, to consider this complex phenomena within some defined boundaries. And it's sometimes easier to understand, for instance, the flow of sort of matter and energy through that system. And even in the younger elementary grades, starting in around 4th and 5th grade, this idea of the transfer of energy through systems it becomes an increasingly important thing. And having a defined system to focus on helps to communicate that understanding and help students to develop that understanding. And then finally, promoting classroom discourse and evidence-based explanations through system modeling. So systems thinking starts out really early in the very primary grades with this notion of just creating drawings about what you're observing and understanding those part and whole relationships. And those drawings can advance into mathematical models, simple mathematical graphs and representations of a phenomena you might be studying that helps you understand that system a little bit more carefully. And through that mathematical modeling, whether it's gathering data or plotting graph points, using that to sort of make a claim about some phenomena that you're studying in the context of your classroom and with your classmates. This notion of promoting discourse and a certain kind of, if you will, cognitive conflict in the classroom it is helpful for students to understand the nature of science, and actually, so when you're really focused on systems thinking and understanding these causal explanations, then and that is more easily done through systems modeling. Okay, so we'll go ahead and move on. So this is another handout that you have in this section, and this is Habits of a Systems Thinker. And I've already gone through, and this actually comes from the Pegasus Institute, I believe. And sorry, and then I actually got this from the Waters Foundation website. So you can see some of the things that I've already talked about, but we live in a world now that really requires students to be systems thinkers, and here you can see some examples here. This idea that systems thinker seek to understand the big picture thinking, bigger kinds of relationships. This idea of servicing and testing assumptions, which I alluded to earlier with this idea of classroom discourse and using evidence-based reasoning. Recognize the impact of time delays when exploring cause and effect relationships, and this is again kind of an important aspect in our real world right now with our complex climate system. Considers both short and long-term consequences of actions, and I won't read the rest of them to you, but this is a handout that you can print out and in reference as you need it. I'd like to take a moment here, now that we're probably roughly about 14 minutes into this, providing you did pause it and actually do the elicitation question, which I'm hoping you did. I'd like to take a moment to do a little self-reflection. This is something that I believe pretty strongly in. I think it really helps. It helps sort of cement the thinking, if you will, reflect, think about some next steps, perhaps how your thinking has changed or been extended, or maybe some of what you've just heard has resonated with you. So if you could go ahead and take your notebook and your pen or pencil and write these two prompts down and then answer them, or you can just answer them. This first prompt actually has a typo in it, but let me read it to you the correct way. What are two ways in which what are two ways in which you can bring systems thinking into your classroom? So consider your current instruction, and I'm thinking science centric here. What ways can you increase and develop more systems thinking in your classroom? Second one, this is more specifically about you as an individual, but how do you use system thinking in your everyday life? Hint, you can reference the Habits of a Systems Thinker handout that we used earlier. So please take a moment to answer those two questions, and after you've finished, the next section, just to do a little preview, we're going to go more specifically into a tool to help you think about how to actually frame a system that you study in your science classroom, and how you can perhaps better teach that system in your classroom.